Hello everybody, this is my first video on SAP 2000 version 14 and it's basically prepared for beginners, but however, even if you are not a beginner, I really advise you to follow me step by step because I will explain it in a simple and a very good way. So let me start the explanation. Before starting the tutorial, please take a moment and go to the subscribe button below and click it, and don't forget to like and share the video. So in this video we will see how to draw shear force and the bending moment diagram using SAP 2000. The version can be any version, but however I am using now version 14, so I selected this version because it's usually at hand for most of us. So this is the beam that I am going to draw for the shear force and the bending moment diagram, and there's a load uniformly distributed from the end 1 up to 4 length meter, and there is one concentrated load and it's acting at from here 5.5 meters, okay, from this end. So this end will be our reference because here X and Z are joining here, so this will be our 0 0 coordinate, and X will be here positive in this direction. So the total length of the beam will be 7.5, as you can see it here. So I think I have to go to SAP, so we can open SAP 14. This is SAP 14, and here I think I have version 21. However, I will give this video using version 14. There's no much difference, and so this is the screen that we get when we open the SAP 2000 version 14. Here we will click on next, then you can say this one okay, whatever it is. This is just tips. So our first and mandatory step is that we have to fix always the units here. So let me go to the units, click on here, then I will select the units that I am interested in. So for this example, kilonewton for the measurement of distance, meter for the measurement of temperature, degrees Celsius. Now you see the color here is in blue, so after correcting the units here we have to remove, you see here the color is blue, so to remove this color click on this black screen, then it will be now white. Now even if you rotate the middle cursor, it will not affect the units. However, if it's blue and if you rotate the cursor, it will cause a problem most of the time. Now kilonewton meter selected, then click on the black screen, then now we go to new file, new model. So here new model can be selected using you first click on the file, then new model, then done, or the shortcut is here, so you can click here. You will have this templates. So from this, now since I'm going to analyze a beam, I think I will select this one, beam. Now here it will ask me number of spans, and the number of spans, I have only one span, so I will insert one. The span length, then here 7.5 meters, and now I have to edit the grid. So here let me tick here, check here, then edit the grid data. Here you see it automatically created grid A and grid B. Grid A is here in this location, and grid B is here, okay. So now grid A is here at negative of 3.75 in the X data. Here you see it's X grid data, so it says minus 3.75, but we know that our grid A is at coordinate 0, so we will insert 0, and at B we have 7.5. The other coordinates are 0 0. We will not change it. Why? Because here Z is above this, at this location Z is 0, and above this it will increase. But since we don't have another storage here, only this beam, so this beam is resting on z equal to 0, and if you view it from the top view, you will see the y-x plane and the y value is 0. So here we will insert 0 0 by default. Now we will say okay, and here beam default, we will not change anything, and we have to make sure that this element is checked, and okay. Now the software automatically creates a beam that is simply supported. Here you will have a pin support, and here you will have a roller support. So but in our example we have a fixed support here, and we have a pin support here. So we have to correct this. So now select this element, this point. Now go to assign joints, restraints. Then I will select the fixed, then I will say okay. Now you see it is fixed here. Now let me select the other one, select, go to assign joints, I'll go to the restraints, then I will select this, the pin support. You see here, this is translations, this is rotations. When I select the fixed, there's no rotation, there's no translation, because it says restraint in joint local directions. There's no translation, there is no rotation. But when I select the pin support, the rotation is allowed, but no translation is allowed. No translation is allowed. So okay, now you see that it is pin support here and it is a fixed support here. Okay, well, let me define the loads. I will go to the load pattern. Now this software automatically have this dead load pattern. So now what we have here is, in our example, is this load is an applied load. The self weight of the beam is not considered. So here, now the dead load, the type is dead, self weight multiplier here is 1. This number 1 is used in this software when we want to consider the self weight of this beam. But now in our example we don't want it, so we will make it 0, and here we will go to here, modify load pattern, then we will modify it. So now we don't want the self weight of the beam. What you want is only to consider applied load. So let me write applied, and the load type, let me select others. The self weight multiplier is 0, and I will say add load pattern here. If I don't want the dead load, I can select it here and I can say delete load pattern if I want. However, it will not affect our calculations because now we made the self weight of the element not to be considered. So let me say okay. Now we have defined the load, and now let me assign this load on this beam. Here we will start the game. So let me select the beam. Always when you are assigning loads, you have to first select the element or the joint that you are going to apply the loads on. So select this beam, and I will go to assign, I'll go to frame loads, then I'll go to the distributed load. If you see here, this beam, it is loaded from 0 up to 4, and it's loaded from 0 up to 4 with uniformly distributed load, but after that there is no uniformly distributed load. There's only one concentrated load here at 5.5 meter from the 0 0 coordinates. So we will apply from 0 up to 4 a uniformly distributed load, and after this it will be 0. Then we will apply the concentrated load after that. So let me apply them one by one. After the selection of the beam, I will select here load pattern, it's applied. Then I can select I can keep it this one as it is, replace existing load, because we don't have already existing load, so there's nothing to be replaced. So I can leave it like that. This is force, so it's like that. Global, yeah. Gravity direction, yeah. Now here you have two options, trapezoidal loads or uniform loads. If I select the uniform load here, the loads will be applied from this end up to the last point here, but we want only from this point up to 4 meter length, right? So we have to we should not select this one, we should go to the trapezoidal load. So here you have two options, relative distance from end I or absolute distance from end I. If you select relative distance from end I, it means this software considers this length of the beam as 1 meter, and you have to divide the length on which the load is distributed to the total length, and you will put that ratio in these distance locations. For example, if your load is from this point up to the center, it means half, right? So 3.75 divided by the total length will give you 0.5. So you will say from 0 to 0.5, and you will apply your loads here. But if you select the absolute distance from end I, and this is what I usually do, you will just directly write the actual distance from end I, because end I is here and end J is here. The initial point is here. So from end I absolute distance, at 0 it's how much, at 4 it's how much. Then these two elements will be filled with the appropriate data. Now here we see at 0 you have 15, and at 4 we have 15, and after that we don't have any uniformly distributed loads. So at 0 you have 15 kilonewton per meter, check the units always, and at 4 you have 15. So I think this is the uniformly distributed load. Now I have to apply the concentrated load here. So again, select the beam, go to assign, go to frame loads. Now we will select the point. In the previous one we selected the distributed, now we will select the point. Then again select the load pattern name, and now if I select now here replace the existing load, it will delete this load and it will only apply for me the concentrated load. But now I will say add to existing loads. Then now again absolute distance from end I. For this one I will only select one point, that is 5.5, because the distance from here up to here is 5.5 from this end, so 5.5 it is 40 kilonewtons, and I will say okay. Oh, I think it looks like the uniformly distributed load has just disappeared, but no problem with this, because it does not mean that your beam is not loaded with a uniformly distributed load. How can we check that? There is two ways. Either you can right click the beam, go to the loads, and you can check here. It says applied point force 40 kilonewton at 5.5 and distributed load from 0 up to 4 15 kilonewtons here. This is one option. The other option is you can go to display and you can go to load assigns and frame cable tendon, and you will select the applied load. Then you have to show you have to say okay, and you will see the complete loading of the beam. Now the next step is to run the analysis. So to run the analysis we have two options or three options. So one of them is just go here, then click it, then you will get the options and you will run. If you don't have this shortcut here, you can go to analyze and you will get the same icon here, same option. Now you have these three load cases, okay, but we only want the applied here. For this example, the date and the model is not required here, so we will say here it says action run, but we say do not run. Now we changed it, do not run. Now we will say the others, run. It will ask me to save the file, so I think I will save it now, because this analysis must be first saved, then let me call it tutorial 1, then okay, then it will save and it will give us the analysis results. Now here you have two windows, one on the left and the other on the right. If you want to make active any of the two windows, just click on the window and it will be active. Now if I want the left one, I will click it and it will be active. Now this is, it says here, the deformed shape due to the applied force here. So let me select the XZ view. Now this is the deformed shape of our beam due to the loading that we applied. Actually it looks like it is so much exaggerated, because if the beam is deflecting this much, it will not fulfill the serviceability limit state. So this is just an exaggerated view. It's only to show us, to give us the hint how the beam will be deflected when it is loaded with such a loading. Okay, so if I want to return it to the previous view, I can go here, show undeformed shape, or I can click only, I can press F4 and it will be okay. Done. Now our last step is to draw the shear force and the bending moment diagram. The software will do it for us. Now I can go to this shortcut here. If you don't have it here, you can go to display and you can get it here. You see here. So let me use the shortcut now. Here, then you will say frames and cables. Now you have here the load case or the combination name, and we will select to draw the shear force. I will select shear 22. Why is that? Why not shear 33? Actually this software understands the coordinates, even though it is showing me here x and y and z, x and z here, and here also you can see it is x, y, z, something like that. But however, it internally reads as x1, axis 11, axis 22, and axis 33. Axis 11 is the longitudinal axis that passes through the centroid of this beam. Axis 22 is in the direction of the vertical direction, that is for the beams it is in the z direction, and axis 33 is in the horizontal direction, that's the y axis. Now our loads are in the vertical direction, so our shear that we are interested in basically is the vertical shear. So the vertical shear is in axis z, that's basically axis 2. That's why we say shear 22. And here scaling automatic and options, fill the diagram or show the values on diagram. Usually this one will give you the diagram together with the values. So let me say okay. Then you see here the shear force diagram, and here you see the values minus 68.16 and here something. Now I think this one is clear. To draw the bending moment diagram, the same step, click here, frames and cables. I will go to M33. Why? Because the bending moment is in the perpendicular direction to the bending direction, right? If the bending is downward, something like this, so the bending moment using the right hand rule, it will be in the y direction. So the y direction is 33 axis. So show the values again, say okay, this is our bending moment diagram. At the support minus 101.21, and the span or the positive moment will be 63.68. I hope this one was very easy. If you have any comments or suggestions or questions even, you can write for me in the comment box. Please don't forget to subscribe to the channel. It is very simple task for you, but it is so much important for us. So thank you. See you in the next video.